at yesterday, and I would like to show you some more details, focus mostly on roots. But when discussing roots, we are always discussing whole trees, as any other organs. When we discuss crowns, we are also discussing roots, and vice versa. So, well, here is just a scheme what we can, what we have at disposal. Well, when discussing crown like this, we mean leaf distribution, for example. When discussing roots, we have also a root distribution in the soil. Then we have vessels in the stem, which we can also analyze as individuals. And then we have radial pattern of sepal. I was discussing yesterday. So, just one more thing about crowns.
I'll get it on the screen.
When we want to describe the conductivity, so one way is also to use very simple calculation first of potential transpiration out of meteorological data, and then compare it. Well, so when we want to describe the behavior of trees without the impact of weather, so we can calculate potential evapotranspiration, and then for the same day, we will calculate the sepal in particular tree. So let's assume that we have potential transpiration per 1 square meter of the standard stand. That's, let's say, nice weather, it is 5 millimeters. And then we measure sepal rate in trees, in a particular tree or their group or whatever you like. So, for example, we can measure, say, 100 liters of sepal rate per day. So, if we have these two data with this complicated mathematical expression, we can say that this tree behaves like 20 square meters of the standard stand here. So this parameter we call simply effective projected crown area. This is very simple, but it works. And of course we understand that this standard stand is not of spatial form. It's a flat form. It's a shortcut glass. So I discussed yesterday how we calculate it, but here are some more pictures about that. So you can see that when we consider radiation measured on a flat area, and we relate it to two trees. One is dominant and one is suppressed. So we can see that suppressed tree goes very well with a global radiation. That means this flat area. A dominant tree deviates. Then, sorry. Okay, when we will take circumglobal radiation, then the linear relations is with the dominant tree, and the suppressed tree is deviating. So because this all can be easily measured, so you can apply it for stand level as well. Well, now a little comment to the stem. Well, we know that we have stems of different form for different reasons. Here it is, for example, impact of snow, and this is straight, and this is caused by lightning. You see the tracks of lightning which hit the top of the tree and went down along the vessels. This is, for example, Syringa vulgaris stem, very rounded. And this is a cause of turbulence of the severe wind in northern Sweden. This is just to show how how stems can vary. Of course, they have also a different vessel distribution. And this is, for example, an oak tree. You see highly conducting large vessels, and little conducting small vessels. And this is the same, a similar picture showing behavior of Laurus azorica. Okay, so there are some technical details which I will not talk about, but we tried to compare what is maximum Seplow or conductivity of the vessels in stems. This is this picture. And these are vessels in petioles. So if you look at it, this value is much higher than this one. But what is interesting, if you compare different species, okay, so this is this situation. And if we compare it with the value which we measured using thermodynamic methods for the whole stand level, so this value is very close to this one. And of course, differs from this one as well. And this situation is valid for both species, Laurus azorica, and which is from Canary Islands, and Quercus robur, which is from Central Europe. So two very different species growing in very different conditions. They have these parameters almost the same. So this is just on the stand level when we calculated that this oak has a leaf area index about 5. That means 20 million leaves per hectare. And this was a theoretical flow in the stems and theoretical flow in petioles in millimeter per hour. And this is maximum measured flow. We see that, of course, this is much higher from both, but this actually measured flow is almost the same like the theoretically calculated for petioles.
That theoretical flow you estimated with 18 Poisson with the fourth power of the diameter?
Yes, okay. Of course, yes. We come with vessels and calculating flows from the fourth power, plus this Hagen-Poiseuille flow equation. Yeah. Okay, so Laurus is similar, but I mean larger. It has a higher leaf area index, about 8, 40 million leaves per hectare, 700 million vessels in stems per hectare, and 8.2 billion leaves in vessels in the petioles. Okay, so they are high numbers. If you look here, of course this differs, but nevertheless the ratio is similar. So in this case, the flows in theoretical flows in stem is about 40 times higher than the theoretical flows in petioles. And this is true here also. And also the differences between flows in petioles is about 5% compared to maximum measured flow. So irrespectively of these two species differences, they behave almost the same way. And it is very interesting because let's assume that if only 5% of conducting vessels are enough to supply maximum transpiration over the whole growing season, that means that 95% of the stem can be rotten. And this is a dangerous situation, especially for arborists, for example, okay? The arborist will come and will see the nicely developed crown, but if he will not measure how look stems inside, he may be wrong that it is a nicely growing tree, because the tree can fall down next day due to wind or so. So it is a tricky and dangerous situation. Well, we have discussed above ground, so now about below ground, which is, of course, difficult. And we have some methods which can visualize root systems. And or some methods can be used for measurements. So we have this possibility of root measurements, the coarse roots using acoustic method. We can use ground penetrating radar. Again, the radar can see roots of a finger size, roughly. Yeah? just only rarely smaller ones. So they are skeleton roots, fine, they are good for conducting, but not for absorbing water, because water is absorbed by fine roots, fine root tips. Okay, then I have shown you some pictures of excavation using the supersonic airstream, and also some methods can derive root distribution using the electric conductance. We have shown it yesterday. Well, we are preferring these two types of methods, which are giving quantitative results. We have over liters per tree, per different root or section, and or measured absorptive root area directly. And of course, because no method gives you 100% results, so it's necessary to apply at least two methods. So this just fits to this situation. Okay, in general, you can meet root systems of two, which are adapted to two situations. Or you have shallow roots, shallow rooting depths, because you may have a rock here or some super saturated water, super saturated soil by water. So there is no oxygen, the roots cannot go there. Or you may have a deeper soils, and then the root system is rather small, but it goes directly to the water, underground water level. Of course, out of this structure depends on their mechanical stability and as well as sensitivity to drought stress, for example. It fits to practically all species. You see, we have, for example, spruce, which is known as shallow rooting. Pine here is known as deep rooting, but here it is on the peatland, and the rooting depth is 5 centimeters. Here is oak, which is known also because of deep rooting species. But here it is in Białowieża National Park in Poland, and here's the rooting depth of the tree over 1 meter in diameter was 20 centimeters. Here is an example of pine trees. Contrasted to that one, it has root length 3 times the height of the tree. Here's spruce tree, which have roots going down to 3 meters. And here's again one pine. So, in general, we can characterize, say, different root areas. Let's say absorptive root area is approximately around 1. It can, of course, differ, yes, but if somebody would ask you, can say this number. Then we have fine root area, which is higher, but these roots are not absorbing. Some people suppose that they are, if they are fine, they are absorbing. Not. But only their tips are absorbing. Then we have mycorrhiza roots, which are much larger, but they are also not absorbing much. They do, but their transport goes along their surfaces above the root hairs, not through the symplast. And because these roots supply water to the absorptive area of root tips. And only through root tips it is absorbed, because only the xylem conductivity is made so big that it can absorb this amount of water. It can transport this absorbed water. So it will not be able to absorb so much water, which can theoretically provide fine roots as a whole, including the suberized part and or mycorrhiza, which is still much higher. But this is just an example of how differ roots. You see here you have superficial roots, here you have thinkers. And thinkers are branching on the level of water. In this particular case, it was a tree growing at the shore of the lake. And when the water decreased, so only under such conditions these roots were visible. Otherwise, they are underwater. Well, this I have shown you already. I want only to mention that this was we just opened during experiment when we measured the impact of tractor movements in the forest stands on root systems. And this colors means which roots were touched by the tires or appeared below the tires in shallow depths. The superficial roots were growing down to the depths of about 20 centimeters, and only in places there were sinker roots growing to the depths of about 75 or 80 centimeters. So this is just to illustrate the variation which we can meet. This is another part of the root system which was opened. And just to have an idea how difficult it is. So we opened all this area to the depths of 40 centimeters within 6 hours using the air spade. So if you will do it by hand, you will spend a lot of your use. Just as funny things, one root was meant to go here, and we measure it. But when we opened this area, so we found out that the root goes like this, and here, and it's somewhere here, and its length was larger than the height of the tree. Sometimes I use methods to measure root area or dry mass usually, unfortunately. And people are sampling, say, using the tubes, and they are sampling the volume of soil, including fine roots and also skeleton roots. But there are places, for example, look here. Here's a gap. There are no roots of these dominant trees. But there are other places like here, and here is plenty of fine roots. And probably the researcher will not sample through this root, this soil. So these are just errors which are arising from sampling technique. One of the very sophisticated technique is microrhizotron. It gives you nice data. You can see roots which are touching the tube, the glass tube, and there is moving camera and making a picture, and you can see individual roots growing there and so on. But problem is that the diameter of the tube is 5 centimeters. And usually you, for forestry purposes or for hydrology purposes, you have at least 1 hectare of the area. So how much stand area represents this tube? So it's a nice method, but always it should be combined with some methods which measures much larger area. So this, as I mentioned, can be done by 2 ways. This is one way when that we measure radial pattern of sapling stems. So here you have a pith, here is a cambium, and there are 2 trees of the same species growing side by side, and this tree was damaged. I mean, its superficial roots were damaged, and also the stem bottom was damaged. This is a healthy tree. So this means this line corresponds to the water supply by superficial roots, and this here by sinker roots. Sinker roots were not damaged in any of these 2 species, of these 2 trees. Well, and this is what we are doing. Let's assume we are measuring. These points are points of measurements using multi-point sensors, yes? And this, again, this line can be separated into 2 Gaussian curves using the mathematical approach, and this, again, correspond to superficial roots, and this correspond to sinker roots. And they are behaving in a quite different way. So, for example, here, it's one day measurements, and this is the measurements the next day under drought. Okay, so severe drought in start to decrease dramatically, and within I think a week it was somewhere here. This is another example. This is a seasonal record of sap flow rate, one peak, one day. And until this point, there was enough water in soil. Then there was a severe drought for 3 weeks. Of course, sap flow rate decreased. And when we look at the radial pattern of sap flow, it was like this. So at the beginning, this blue line, this corresponds to superficial roots, and this to sinker. That doesn't like it. These are sinker roots, yes? This blue line. So this represents about 20%, and this represents about 80%. Now, after 3 weeks, this decreased, and it was less conducting water than this. And this sap flow rate from the deeper roots increased a little bit. It's compensating the lack of water on the surface soil. Well, once we measured in southern Portugal the Quercus suber, and this was an area which was green in the springtime, but became dry during 2 next months. During summer it was completely dry and no plants surviving. But trees were transpiring a lot of water. So we are looking what's the situation, and we find out, fortunately, nearby an open mine for sand, and this was about 10 to 12 meters deep, and the roots were going there, and until they reached this layer of soil, which was wet. It was again a dry soil, and here was the next wet layer. So in principle, these roots are based on this water in the depths of, say, 10 to 12 meters. What is very important, this is just a scheme of the so-called redistribution of soil water in roots. So let's assume that you have a situation that there is enough water. Fine. The most water comes from superficial roots and less water from sinker roots, because there are higher resistances and it takes more time to transport water. But this soil, this upper soil can be easily depleted during drought, and now trees dependent only on this superficial, only of this sinker and or tap roots. So water comes through the tap root, like here, and here it separates. Some water goes to the stem and for transpiration. Some water goes to this root, because there is still remaining high water potential, or high suction force, low water potential. The same is happening with this root. Again, water stream is divided here and here. So in this part between these two roots, water flows at the same time in two opposite directions, in different layers of the sapwood. After rain, water comes usually from the surface. Okay, so this is wetted, and again, part of this water goes to transpiration, but part of the water goes down, and this resupplies this underground water level. So this is just an important mechanism for tree survival, and it's much more widespread than it is known. Well, some results of watering which we apply. So this was done during experiments with tractors. We watered this part, which is shown here by this line, but of course everything was under soil surface, you know, so it was not visible. So we just blindly applied water here, and it was this moment. You see, water in one of these roots increased immediately after watering, while the water in other root here, it decreased. This was water which was not. which was not watered. Again, you see the water moved in direction of stem, and here, because this root was not watered, it was drier, and its water potential just use this water, he sucked it to itself. This is very, very tricky because it allows to keep the whole conducting system, the whole root system working. No roots will be killed by the drought due to the help of other roots. So it is very clever, and we should have it in mind when discussing some human relationships. Well, so this is finally the electric method for absorptive root area measurements. This is a scheme. I am not going to show you to go into details. For this, who will be interested, I can show you all system outside. And this is the main equation which is used. So this is sensitivity of the stem and so-called critical distance, and this is a difference in Earth's impedance of the stem. So this is just to show. Then what we are actually measuring. So we are measuring these root tips, because until here the root is suberized, and the main diameter of the root is 0.42 millimeters, so very narrow. Some people, and root people, unfortunately, they say, well, I'm recognizing fine roots below 3 millimeters. The other ones say, no, me recognize fine roots below 2 millimeters. And there are discussions. Nothing is true. Look here, we measure it for spruce at least in two sides. They're absolutely the same lines, absolutely the same diameter. Okay, so we are measuring it. When we measuring this electricity on the roots, just to show you differences, we measured simultaneously one Douglas fir and one spruce. Spruce were growing in a wetter soil, and this was growing in drier soil. So we see differences at this scale, at this height. And so these are the input data which we use for further calculation of root area. Some examples. Well, let's say we measured two groups of trees. One was growing on a sufficiently wet, deep soil. This was on shallow soil. And what is important, when we measured total fine root area, say by scanning, okay, so we receive these two columns. This is one side, this is another side. Then when we measured roots using microscopy, we have got these results. One side, another side. And when we measured using Earth impedance, we have got these values. So if we take a mean, so roughly 2/3 of the anatomical, that means potential flow, was measured as an actual flow by electricity. Okay, only just final examples. Trees were planted on these rows, and because the soil was very wet, it was in everywhere. And you see that along these, the roots were developed much more than across, because there were some layers which were completely watered, and it was difficult for roots to grow there. They can do it only if there were a very dry year. There's another example, the alley of the oak trees. And so across, here was a road where roots were cut by bulldozers when the road was built. And here was a fence, and there was a pavement, the loamy pavement, which was very much used by tourists. And the soil was compressed, and here was a small slope with all water falling here, went here, and here it evaporated. So this was mostly wet soil and compacted, and also contained some more salt during winter time. Okay, this is an example of the tree. We measured sepal rate in this tree from two opposite sides. From one side, it shows these high values. From other side, very low values. So difference about one order. And so it was very surprising for us. That's why we opened this tree by the airspace. And we find out that really from this side, the tree has such deep taproot and more roots than from the other side. Why? Because we find here underground the remnants of the old stump. It was a neighbor tree which was originally larger than this Douglas fir, but Douglas fir was more powerful, and as soon as it goes above it, it was killed by this tree. Well, so this is in general just rough illustration what we can get when measuring in the field, and of course then we can combine it these values of sepal rate, that means which we have in liters per tree or per root or per section, and we can combine it with absorptive root area and also with leaf area. So we have all this at disposal. These are input data, and which can be further used for calculation and better characterization of the tree, any species under any field conditions. Thank you for your attention.
Thank you very much for the workshop. I wish we had time to do an outdoor component, but unfortunately we did not. Are there any questions for Dr. Jan Cermak? We have a question in the back. I saw a hand raised. I thought it was a question.
How long takes to measure the roots of one tree with your method? How long, how many hours or how many days takes to measure that?
1 or 2 hours, one tree, for two people.
Okay.
If we are measuring it from 4 sides, okay, cross. Say, that means downhill, uphill, or to the south or north and so on. It doesn't matter. Whenever you like, you can measure it. We are usually using 4 sections, like this, okay? And in these sections, we are measuring the roots. The section is given by the positioning of electrodes.
If you have different species in the same stand,
Yeah,
can you separate?
Yes, easily. Also, different trees of the same species growing near side by side. Just because the system feels only the tree where we put electrodes.
Ah,
okay. So, and this, at the same time, we can put, gradually we can put electrodes on the tree, on the stem, which then we are getting integrated values for the section, okay, or for the whole tree, and or we are measuring separately roots. In this case, we use mostly sepal rate, and when measuring in stems, we are combining both methods, like here.
Thank you.
We have another question from Bandana. Yes.
So, thank you very much. It's very interesting. I just want to know if there is a, this root like in ficus in the ficus species, like a prop root or prop root, the roots above ground. Do you consider those?
You see, well, this system measures the living, the functioning roots.
Yeah.
If the tree root is dead,
No,
so then it behaves like soil. It doesn't see it.
No, I'm asking if the root is underground, and there are some species they are also having root above ground, like in ficus species,
Yeah.
like prop roots.
Mangrove species, yeah.
Yeah. So for that, do you consider those also?
Of course. It doesn't matter where are the conducting roots. The system, because they are, you see, they are conducting roots which are covered by bark, and they are usually not absorbing much water. But it measures just root tips, which are at the end of fine roots. Okay? And these root tips are usually underwater or in close contact with water. they cannot grow much longer time underwater because of lack of oxygen. They will die, or they will simply will not work. So if it is, if you have a tree which is flooded, yes, due to say beaver activities in the forest, beavers make a dam, and then you have a nice lake, and all trees which will remain in the lake, they will die. So this is just an illustration of the situation.
Thank you very much, Dr. Cermak.